All right, welcome everyone. Welcome to our fifth lecture of the semester here. So previously on Calculus 3, what we've done is we started by talking about three-dimensional space and how to use the coordinate system there and how that stuff works. And then we began talking about vectors. Remember, vectors are mathematical objects with not only size or magnitude, but it also has direction as well. And they're often going to be pointing to our position at a certain time. And then we learned about how vectors work and how to multiply vectors together in two different ways. And today what we're going to start doing is we're going to apply some of the stuff that we've learned thus far. And we're going to apply it to learning about different kind of curves and shapes and surfaces that you can have in 3 dimensions. So we're going to be using all of this vector knowledge to help us with that. All right, so why don't we start off with one of the simplest curves. It's kind of a weird thing to call it because it's a line, but we're going to start by talking about lines. And when I say curves, I mean like a one-dimensional, you can almost imagine it as like a string. Just because it's perfectly straight doesn't mean it's not a curve. So curve doesn't have to imply bending of any sort. So this straight line right here, I'm going to count that as a curve here. Okay, so let's say we want to have an equation of a line in R3, and we could still have one-dimensional objects in three-dimensional space, just like it's drawn here. We don't need to have everything be two or three-dimensional. We can have one-dimensional stuff as well. So how do we define a line in R3? Well, how did we define a line before? We defined a line by having a point and a slope, or at least that was one way of doing it. And effectively, we're going to do the same thing in R3 right here. So this is going to be our point that's going to lie on the line. So that's right here. And then we have this vector v, which has these components. This vector needs to be parallel to the line. And a way to think about this vector v, you can imagine this almost as like the slope vector of the line. So we see you have this vector v, and if we move it up, it will move along this line right here. So the way I like to imagine this is it's the slope vector. For every unit we go forward, we go A in the X direction, B in the Y direction, and C in the Z direction. Okay, so with these two pieces of information, any point on the line can be designated as the terminal point of a vector. So we can have these vectors that are pointing to our line right here. So depending on where we are on our line, our vector will change direction. So how do we come up with a formula for this vector right here? What we're going to be doing is we're going to have the equation x plus at. We're going to have y plus bt. And we're going to have z naught plus ct right here. So it's almost kind of like we have 3 separate line equations at once, and we combine them all together to get the equation for our total line through three-dimensional space right here. And so if we plug in t equals 0, for example, we see that this line has x naught, y naught, and z naught, which is good because it's supposed to have that. And then every unit we go forward in t, we move a in the x direction, b in the y direction, and c in the z direction. Exactly what we would want to do with something that we think of as a slope. All right. And then this t right here, I don't know if you guys remember Calculus 2 or not. Hopefully you remember at least something from there. But the parameter t, this is effectively going to be our variable. Which way the vector is pointing depends on this variable t, which is independent of each one of these 3 right here. So we're not going to do it as z depends on x and y or anything like that. We're going to do it as all 3 of these depend on t. Okay, so the vector equation for a line, so there's going to be 3 different ways of writing out our lines right here. So there's the vector equation where we have our given point and then t times our slope, or another way we could look at it is like this, where we have our given point and then we have t, which is our variable, and then we have this, which is our slope right here. And this will end up giving us a line. Now, one thing for all of these equations of these lines right here, there's more than one possible equation. Like for example, maybe instead of using this point as our given point, I can maybe take, back down here, I could take this point right here. And I could just change these coordinates right there, and that would still be a perfectly valid equation for our line. So there will actually be many different possible equations that we can have for our lines right here. Is the vector r of t the line, or is it just pointing to the line? It's pointing to the line. R of t, depending on what t is pointing to different places on our line right here. All right. So let's see here. One thing that we may need a little bit later is we may want to come up with a parameterization for a vector that's pointing at one point at time 0 and then another point at time t equals 1. So it starts at one point, maybe this one right here, we can call it A, and then at time t equals 1, it ends up over here. So one way we could do this, and this might be something we use in the future here, is at time t equals 0, we want this to be our point, right? So I'm going to have 1 minus t times x naught, y naught, and z naught. And then I'm going to have t, x1, y1, and z1. And for this, we're going to limit t to be between 0 and 1 right here. Remember back in parametric equations in Calc 2, sometimes we limited what values of t we would accept. Okay, now why do we have this weird equation, especially why do we have this 1 minus t here? Well, let's plug in r of 0. So at time t equals 0, we're definitely supposed to be at point A, right? We're supposed to start at point A. So if we plug in 0 here, we're going to have 1 times this vector. And then we're going to have 0 times the second one. And so consequently, we're not going to have that one at all, and we're going to be at our starting point. And then as t increases from 0 to 1 right here, this coefficient is going to go down, so this point will have less and less influence, and this coefficient will go up, so this one will have more and more. And then finally, when we get to our last point at 1, we're just going to have 0 for this, and then 1 for this coefficient. So at a time over 1 second or so, we're going to move between this point and this point. And you could definitely scale it to be more than 1 or less than 1. Like let's say I want to take 10 seconds to move there. I would just replace this with a 10, for example. So this is going to be a useful piece of knowledge when we want to construct line segments here. You want to limit t to 5 instead? Would you put 5 minus t? Yeah, that's exactly. Yeah, absolutely right. All righty. Let's see here. So let's move on to our next page here. So this was our first equation for a line right here. This is our first type of equation. All right, so what other types of equations are we going for right here? What other ways will we have of expressing a line? Why did I use 1 minus t here? Because when I plug in t equals 0, this will be 1, and then I'll have 1 times this point right here. So I'll have that point, and I won't have any of this. So that will go away. So just have this. And then when I go to t equals 1, 1 minus 1 will be 0. So we won't have this point influencing anymore. And we want all of this point to be there. All right. So we're not going to use this right away, though. So don't worry. Don't worry too much about this right now. We'll remind you how to do this once we get closer to it. All right, next we have parametric equations for a line. And all we need to do for these is simply take the components of our vector equation and write them down. Because we already effectively had these, right? We have x is equal to x naught plus at, y is y naught plus bd, and z is z naught plus ct. So effectively what we're doing with parametric equations is we are writing down what we had in our vector equation here. So y is going to be y naught plus bt, and then z is going to be z naught plus ct right here. So these are parametric equations, and we're not writing them in the context of a vector here. Okay, so a vector ABC describes the direction of a line. I already talked about this. The way you can imagine this again is you can imagine it as the slope of your line. That's the best way to think about this V right here. Okay, so let's do an actual concrete example now that we have these two types of equations for lines here. So find the vector equation and parametric equations of a line through these 2 points. And there's actually kind of a typo here. So I'm going to cross out the, and I'm going to write A. Because like I said earlier, remember there are many different vector equations you can have that represent the same line. So we're simply going to find one vector equation that represents the line. It's kind of difficult to write down infinitely many, so we're not going to do that. So we're going to find a vector equation, and I'm going to put here some, for the same reason as that, some parametric equations of a line through these two, because we could also have different parametric equations for the same line as well. So we're just going to find one copy of each. Okay, so let's see here. So remember, we need 2 ingredients for our line. We need the point that it goes through, and they already tell us those explicitly. So I guess why don't we just pick A to be our point here. So our point that it's going to go through is 2, 4, -3. And then what else are we going to have here? We need to come up with some kind of slope, right? So the way we're going to construct the slope, actually, let me ask you guys this. How do you think we're going to make the slope vector here, or the direction vector? That's right, it's going to be B minus A. So our V is going to be 3 minus 2. It's going to be -1 minus 4. And then we have 1 minus -3. Okay, and then if we compute this, we have 1, -5, and 4 right here. And so this vector, this is the vector that points from A to B. So this vector will definitely lie parallel to the line that we care about here. So if you ever know 2 points of the line, you could subtract them to end up getting your direction vector, or your slope. All right, so now that we have these, I'm going to write the vector equations for this line. So R of t is going to be x, y, z is equal to, now we're going to have our point as one of these vectors. So it's going to be 2, 4, and -3. And then we have t times our direction vector here. We have a question in the chat. We could also do A minus B, right? Absolutely. Yeah, we could have done this the other way around. We would have had the negative of these numbers, but that also would have been a valid equation for this line as well. So yeah, that's totally fine. All right, so here we go. So we have a nice vector equation for our line. And then now let's construct some parametric equations. But these are also pretty easy to do here because we just take x is equal to 2 plus t. We have y, let's see what that is, 4 plus -5t. So 4 minus 5t right here. And then we have z is going to be -3 plus 4t. And there we go. We have some parametric equations for our lines right there. So we effectively just read them off of our vector equations here. Would A minus B be like the negative slope? Yeah, you can imagine that. Any vector that moves either parallel or anti-parallel to our line, all of those are valid direction vectors or slope vectors. Any of those are okay. Now the t value that will give us specific points on the line, those will change if you change your equation of your line. So those might be different, the t values you get particular points. But if you plug in all of the different t values, you're eventually going to get all of the different points. So there are many different slopes that we can have, and there are many different reference points we can have here. All right, so there we go. So I said there were 3 different ways we were going to express lines. So we have 2 of them now. And then let's see what the third one is going to be here. The third is going to be symmetric equations for a line. So this requires A, B, and C to not be 0. So we can't have 0 for any of these coefficients right here. So if we do that, remember our parametric equations were x is x naught plus AT, y is y naught plus BT, and z is z naught plus CT, right? So what we could do is we could solve each of these equations for t. So for this one, for example, to solve this one for t, I would subtract x naught over here and divide by a. And we're allowed to do that because a was supposed to not be 0. So we have x minus x naught over a is t. And then we could do the same thing for each of these other ones as well. And then we have z minus z naught. And then since they're all equal to the same thing, they're all equal to t, that means they're all equal to each other. So we have x minus x naught over a is y minus y naught over b is z minus z naught over c. So where we have each of the x, y, and z separated and they're all equal to each other in an equation like this, then this is going to be our symmetric equations for our lines right here. Remember, we could set them all equal to each other because they all equal the same thing. They're all equal to t. T stands for time. It often does in applications, but it doesn't need to. T can just be any vector, or sorry, any quantity you want. So you think of it as like a variable, but it's independent of each one of these three. Okay, let's do another example here. So find parametric and symmetric equations for the line through the point 2, 0, -1 and perpendicular to both of these vectors. Okay, now let's think about this. If we want something that's perpendicular to two vectors, how do we get that? That's right, we're going to do the cross product to get something that's perpendicular to both of these. So before we do anything else, I'm going to do the cross product of this cross this. So my vector, that's inevitably going to be our direction vector here. Let's see, we have I, J, K hat. This one has 1, 2, and 0 as coordinates. And this one has 0, 1, and 1 as coordinates. Okay, and by the way, you could have done this the other way. Remember, if you switch the order of a cross product, you'll just get the negative of the answer. But it doesn't matter if we take the negative of our slope. It'll still be valid. All right, so let's see what this is going to be. Let me write this out in more detail. So we have I, and then we ignore this row and column, and we have the minor 2, 0, 1, 1. Now remember, we have that minus sign by default with the j hat, and the other two columns are 1, 0, and 0, 1. Okay, and then finally we have positive k hat, and the things that are not in the same column or row as that are 1, 2, 0, 1. Okay, so if we do these determinants real quick and put them into coordinate form, we have 2 times 1 is 2, and then we subtract 0. So this is 2. We have 1 times 1 is 1, minus 0 is still 1, but then we have a negative. And then we have 1 times 1 is 1 minus 2 times 0. So we get 1 right here. Okay, so this is our vector that's perpendicular to both of these, and we want our line to go in the same direction as this vector right here. So this is going to be our direction vector or our slope, and they were also kind enough to give us a point as well. We know it's got to go through 2, 0, -1. All right, now they asked for parametric and symmetric equations. So let's go ahead and write down the parametric equations. So when we have x, we write down the x point that we go through, and then we do the x value of the direction vector times t. And then we rinse and repeat for the other variables as well. So y has a 0, and we have minus t. And then z has -1, and we're going to have t here. Okay, so these are the parametric equations, and as I like to abbreviate parametric, I abbreviate it as PARM, not to be confused with chicken parm or anything like that. It's parametric equations. So we have these, and then what I'm going to do now to get the symmetric equations is I'm going to solve for t here. So just like I did up here in general. So I subtract 2 and divide by 2. And that gives me t. I simply multiply this one by -1. That gives me t. And then finally, I add 1 here. And that also gives me t. So if we combine all of these together, we get our symmetric equations. And there we go. These are our symmetric equations here. All right, so why did we use the cross product between these two vectors? Whenever you want something that's perpendicular to two vectors, you could take the cross product, and the result of the cross product will be perpendicular to those. All righty. So we got this example done. That's good. Let's move on to the next one here. So in addition to lines, we're also going to have a lot of occasions to use planes as well. And it turns out that kind of like we use vectors to represent lines, we can also use vectors to represent planes. Although we're going to be doing so in a slightly different way right here. Okay, so a plane in space is determined by a point in the plane and a vector A, B, C. So this is kind of like our direction vector again, that is orthogonal to the plane. So before with our lines, we wanted to go parallel to the line itself. Here we're going to go perpendicular. So why do we change things up for the plane? Well, let's say we have another point in this plane, X, Y, Z. So let's take the direction vector from this P naught, this point we know is in the plane, to another point in the plane right here. And I'm going to call this R. That's a usual name for a direction vector here. So what's the relationship between N and R as vectors? You guys can say it in the chat or say it out loud here. What's the relationship between these two? That's right, they're going to be orthogonal. Because this vector lies in the plane, right? Because this point's in the plane, this point's in the plane, so everything in between them will be in the plane as well. But then N was specifically orthogonal to the plane. So if this is going the same way that the plane is, and this is orthogonal to it, that means that there's going to be a right angle in between these guys. Now I saw some people talking about the dot product on the chat here. Remember that if you have two vectors and they're orthogonal, then their dot product is going to be 0. So that's going to be this equation right here. Let me get rid of this. Okay, so I guess I called P naught P that. I guess I called that R. That's another common name for it. So R is this vector pointing from P naught to P right here. So if we dot these together, you're going to end up getting 0 for this because they are orthogonal. That's what we learned the other day with dot products. So let's write this out in a different way here. So what I'm going to do is I'm going to write out the vector P naught P. So if I want to have the vector that points from X naught, Y naught, Z naught to X, Y, Z, that's going to equal X minus X naught, Y minus Y naught, and Z minus Z naught. This is exactly how we did it in the very first problem earlier. We just subtract the final point minus the initial point. And then we dot this, so this was P naught, P1, or just P, sorry. And then N, we said N, those components are A, B, and C. And since these are just different names for this vector in N, remember, the dot product's still got to be 0 right here. And I emphasize this is not the 0 vector. These are scalars. So this is just 0, the number. Okay, so let's actually go ahead and do the dot product. So remember, the dot product is where we multiply all of the matching coordinates together. So I do A times X minus X naught, and I end up getting this right here. So I end up getting that for our first part of the dot product. You can probably see where this is going now. I do B times the Y minus Y naught, and I add it to my result, and I get this. And then I do C times this right here, and then I end up getting this right here. And that result has to be 0. So this first equation up here, where we wrote it in terms of vectors, this was the vector equation for the plane. That's going to be one way for us to represent the plane. When we actually do the dot product and write this all out as one thing, that's going to be another representation of the plane called the scalar equation for the plane. And then finally, let's say we decide to multiply all of this stuff out. So if I distribute the A, I have AX minus AX naught right here. I have BY minus BY naught here. and CZ minus CZ naught here. Okay, so we can rewrite this equation right here as this down here. And this is the third way of writing a plane. It's called the linear equation for the plane. Now, what's the difference between this and this? Well, let's see. So we see the AX, we see where that goes. We see BY is showing up here, and then we see that CZ is showing up right there. Now, everything else, this minus AX naught, minus BY naught, minus CZ naught, none of those have X, Y, and Z specifically in them. So they're all constants. And what we could do is we can combine all of them together into this one extra constant at the end, D, right here. So if you distribute this and then combine all of the constants together and put that at the end, then that's going to be your linear equation for the plane. It's not written here, but another way you may see this is AX plus BY plus CZ equals D. So you may combine them all together and then add them to the other side as well. This is another common form for the linear equation of the plane. All right, and then note the coefficients A, B, and C are the components of the normal vector to the plane, meaning we are orthogonal. And remember, it had to be orthogonal here because we wanted our dot product to end up equaling 0. If it weren't orthogonal, we wouldn't know necessarily what the dot product is going to be right here. All right. So let's see. Let's try to find some planes right here. So this is kind of the theory. Let's go ahead and find a plane. All right. Oh, you guys worried about the sign of this? You could put a negative over here if you were worried about subtracting that. Effectively, I'm just saying you can move all of these constants to the other side right here. That's all I'm saying. Okay, so our first task is to find an equation of the plane through the point to -1, 3. So this is what our P naught's going to be specifically for this one. And perpendicular to the line 1 plus 3t, y is 2 minus t, and z is 3 plus 4t. Okay, now this is a little bit different. They didn't directly give us a normal vector for this. They didn't directly provide it. We somehow have to get a normal vector out of this information here. Well, let's think about what this means. So let's say maybe this is our plane right here, right? And there's this line, and it's going to be perpendicular to the plane. So it's going to cut directly through right here. And if that's the point on the plane, it's going to hit the plane at a 90-degree angle, like that. All right. Now, what does this mean? Well, let's say we have a direction vector v for the line right here. That means that the direction vector of this line is what to the plane? I think I heard someone in the crowd say it. What was that? It's perpendicular. That's right, because this vector v heads in the same direction that the line is, right? Because it's the line's direction vector. So if this is heading in the same direction as the line and the line's perpendicular to the plane, well, then this vector must be perpendicular to the plane as well. So our n for this problem will be none other than what our slope would normally be for this line. Okay, so what's our n here? Let's see, we have a 3 times the t for the x. We have a negative t for the y, so that'll be -1. And then we have 4t for z. So this is going to be our normal vector here. Is perpendicular and normal the same thing? Yes, they have a lot of different names for the same thing. So perpendicular, normal, and orthogonal all mean the same thing. All right, now that we have these two ingredients right here, we can write down the equation of our plane. And just for kind of showing you guys how this works in general, I'm going to write down all 3 different types of the equations here. So the first one is the vector equation here. So that's going to be x minus 2, y plus 1, z plus 3. So it's x, y, and z minus these guys right here. And then I dot that with my normal vector, and that should give me 0. So this is the vector equation here. Okay, so then how do we get the scalar equation? We actually just carry through with the dot product. So we do 3 times this, and then we have -1 times this, and then we have 4 times this right here. And remember, all this stuff is still equal to 0. So this is the scalar equation for our line right here. All right, and then our final equation was equation type was the linear equation. And that comes from just distributing everything here. So I have 3x and then -6 minus y minus 1 from here, and then 4z plus 12 right here. So if I combine all of these coefficients together, or sorry, these constants together, I have 3x minus y plus 4z. Let's see, I have -6, -1, and 12. That kind of sounds like 5 to me. So there we go. This is our linear equation for the plane. And kind of like I was saying earlier, right here, another way you may see this is some people like to move the constant to the other side. In fact, that's actually the way I learned about doing this. So you may also see this as 3x minus y plus 4z is -5. This may be another way that you'll see the linear equation for the plane. All right, wonderful. So there we go. So that's how we find equation of a plane in this case right here. All 3 equations equal each other, right? They're pretty much like 3 different ways of representing the same thing. And they all kind of come from one another because we kind of do the dot product and get this, and we distribute and get this one. So, all right. Let's see. Find an equation of the plane parallel to these vectors and containing the point 1, 2, 3. All right, let's see here. So we want our plane to be parallel to these vectors right here, meaning we want these vectors to be in the plane right here. All right, so remember, we need 2 ingredients to make our plane, and we already, again, have the first ingredient. Our reference point is going to be 1, 2, and 3. And then once again, we need to come up with a vector that is normal or perpendicular or orthogonal to the plane right here. Trust me, it's not just to mess with you guys. It's really annoying doing mathematics at a higher level with all these names too. It's really obnoxious. I don't know who came up with all these names for them. All right, anyways, so if we have these 2 vectors that are in the plane and we want something perpendicular to the plane, how do you guys think we're going to come up with that? That's right. It looks like the chat has it here. We're going to do the cross product. Oh, sorry, the live audience has it too. All right, so let's go ahead and do the cross product of these. All right, so we have -1, 0, 1. And we have 1, -1, 0. Okay. Let's see here. We have a decent amount of stuff left. What time is it here? I'm just going to go speed through the arithmetic for the cross product here to save some time so we can get to the end. So the I component will end up being +1. The J component will end up being +1 as well. And the K component will be, oh, wow, that's +1 too.
Professor Manley.
Yeah, what's up?
Why are we doing the cross product if it says parallel to the vectors?
So these vectors right here, these are parallel to the plane, right? Meaning that they're actually in the plane. So these are in the plane right here. Now, if I cross these 2 together, I'll get something perpendicular to these vectors. And since the vectors were in the plane as well, that means it'll also be perpendicular to the plane. So this is vector 1, vector 2. And if I cross them, then I'll get this vector here, which is perpendicular to both these and the plane, which is what we're going for.
Thank you.
All right, so we got our vector here. It's 1, 1, 1. Don't forget that the J has an additional negative attached to it. And yeah, since we have this, then we could just simply write down our equation for our plane. So we're going to have x minus 1, y minus 2, and z minus 3. Remember, we do x, y, and z minus each of the 3 matching components here. And then we dot it with our normal vector. Remember, that's what this is. This is normal to the plane or perpendicular to the plane. That has to end up equaling 0. All right, and then we could do that was the vector equation. We could do the dot product, 1 times this, plus this times this, plus 1 times z minus 3. That also needs to equal 0 right here. All right, and then finally we can combine all of these together, all these constants, and we can get x plus y plus z minus 6 equals 0. And this will be our plane. All right, let's do one more problem with finding planes, then we'll move on to something else here. Okay. All right, next, I wanted to find an equation of the plane that contains the points P1, P2, and P3. So this time, we're not just given 1 point, we're given 3 points, but then that's it. But the good news is kind of like how you can uniquely identify a line. If you know 2 points it goes through, you can uniquely identify a plane if you have 3 points that it goes through right here. All right, so let's take a look at this. Oh, so what are you guys confused about? I think are you guys confused about something here? Are you still wondering about the cross product here? Yeah, the plane parallel. Okay, so imagine that I don't have anything to do that with. Yeah, here's essentially the picture of what's going on. This V1 and V2, these are in the plane. So if you're parallel to the plane, you can move these vectors so that they're actually in the plane, right? And so remember, our whole goal is to get a vector that's perpendicular to the plane. That's what we need for this n right here. So if these vectors represent stuff that's in the plane, and we can take the cross product and get something that's perpendicular to the plane, then we're going to use that cross product as our normal vector here. So if we cross these two, we'll get something that looks like this. And because these were in the plane or parallel to the plane, this necessarily will be perpendicular to the plane. All right. Anyways, let's go to this one right here. Let's take a look at, so what we're going to do is we're going to do essentially the same thing that we did in the previous problem, only this time we're going to make our vectors from scratch. So we kind of had these vectors given to us in the previous problem. We're going to make some vectors in the plane for this problem. So I'm going to make the vector that points from P1 to P2, and that will necessarily be in the plane, because both of these points are in the plane. All right, so I do 0 minus 1 is -1. I do 2 minus 0 is 2. And then I do 1 minus 1 is 0. Okay, I also need to use my third piece of information here. So I guess I'll do P1 to P3 right here. So we do 1 minus 1 is 0. We do 2 minus 0 is 2. And then we do 3 minus 1 is 2. All right. So whenever you have vectors connecting 2 points that are in the plane, these vectors are necessarily parallel to the plane. And just like in that last example, so you can imagine these 2 vectors we made are in the plane right here. If we cross them, we'll get something that's perpendicular to the plane, which is what we want. All right, so I'm going to cross these guys together. I, J, K. All right, we're going to have -1, 2, and 0. 0, 2, and 2. All right, what's going to happen here? So for our I, we're looking at this box. We have 2 times 2 is 4, minus 0, 4. For the j, we're looking at these two columns here. We have -1 times 2 is -2, minus 0 will be -2, but then the j gives us an extra negative. And then finally, we have -2 here minus 0 here. That's -2. Okay, so this is going to be these vectors crossed together, and this is going to be our normal vector. This is going to be the thing that we're going to use to define our plane. Can we use P2, P3 for the second vector? Absolutely, you can use any combination of these because all of them will be in the plane right here. So yeah, you could use any combination of them. And you would definitely get different cross products though. So you may not get the same thing that I get right here, but whatever you get should be a multiple of this. So yeah, whatever you get, no matter how you kind of set this up, should end up being a multiple of this right here. All right, so we have our normal vector, and then we could just pick one of these to be our representative point in the plane here. So I might as well just use P1 here. So P1 is 1, 0, 1. All right, so then that means our plane equation right here is going to be x minus 1, and then we have y minus 0, so just y, and then we have z minus 1. I dot this with my normal vector, 4, 2, -2. And remember, since these vectors are inside the plane, you can imagine these two vectors like these ones right here. If we dot it with the normal vector here, you should end up getting a 0 right here. All right. Why are these in regular parentheses? Because this is a point. So usually with points, we just write them with these parentheses right here. All right, so I'm going to dot this. I have 4 times x minus 1, and then I add 2 times y. And I have minus 2. We get z minus 1. All right, there we go. So can we use any point for the dot product? Yes, so rather than 1, 0, 1, we could have used 0, 2, 1, or 1, 2, 3, or if you came up with another point on the plane, you could have used that as well. All of these are okay. Just like lines, there are actually many different equations for the same plane. All right. So let's see here. Let's move on to a definition right here. Two planes are said to be parallel if their normal vectors are parallel, meaning that one normal vector is just a multiple of the other. So why does that work? Let me draw a better picture. Let's say we have this plane and then we have this one right here, which is parallel. If we look at our normal vectors, they're going to be pointing in exactly the same direction because these planes are oriented in the same way. So at most, one can be a multiple from the other right here. So that's what happens when they're parallel. And then two planes are orthogonal if their normal vectors are orthogonal. So if I maybe have a plane that's kind of going the opposite way here, like kind of cutting through this one, kind of like an X shape here. If I look at that one's normal vector, then that's going to end up being orthogonal to the one we had before. So all that means is that whenever we want to know the direction or orientation of a plane, we simply just need to consult its normal vector. We don't need to worry about any of the other stuff. Don't need to worry about the specific points. We just look at the normal vector. All right. So determine if the following planes are parallel, orthogonal, or neither. So let's see. So let's write down the normal vector for this one. So let me ask you guys this real quick. What's the normal vector for this one? And then what's the normal vector for this second plane right here? Absolutely right. Okay, so we have these as our normal vectors. And remember, it's really easy to read them off. You simply just read off the coefficients that are next to the x, y, and z right here. Okay, so let's think about the first question. Is one of these a multiple of the other? Can we multiply this one or this one by a number and get the other one? Yeah, it seems like the answer is yes here. And moreover, it seems like that number is -5. So if I do -5 and 1, well, -5 times 2 will be -10. -5 times this will be +15. And then we get ourselves -30 right here. And that is N2. So these guys are parallel. Okay, let's take a look at the next batch here. So our N1 is -1, 3/2, and -3 right here. Oh my God, I just noticed now that the Rita has a cat. That's a very nice cat. Anyways, sorry for the people here, you can't see it. N2 is going to be 3, 4, and 1. All right. So let's see. If this is going to be a multiple of this one, it would need to be -3, right? Because -3 times -1 will give us the 3 right here. But if I multiply -3 by the other numbers, like maybe this one right here, it's going to give me 9 over here. But instead, I end up having a 1. So these are definitely not multiples of each other. So why don't we try the other thing that we could check here, and we could dot them together. Maybe if this is 0, they'll be orthogonal. Okay, so I have 3 times -1 is -3. 4 times 3/2 is 6. And 1 times -3 is -3. And lo and behold, these do actually add up to be 0 right here. So these guys are orthogonal. All right, these are parallel, these are orthogonal. I bet you guys could probably just guess, by the way this is structured, what the last ones are going to be, but let's take a look anyways. So the normal vector here is going to be 1, 1, 0, because we don't have a z at all. And 2 is going to be 0, 1, 1. All right, well, since we have a 0 here, if we multiply this by anything, the last component will still be 0, but that's clearly not the case over here. So there's no way that these guys are parallel. Let's dot them, see what happens with that. Zero, 1, 1. Let's see, 1 times 0 is 0. 1 times 1 is 1. And 0 times 1 is 0. So this gives us 1, but unless you want all of math to crash, 1 is not equal to 0. So that means that these guys are not going to be orthogonal right here. So they're not orthogonal, they're not parallel. So I guess they're neither. All right, so the point is that you can look at what a plane's doing by looking at the normal vectors here. Let's see here. I feel like I've been going through this pretty fast, but we're still not quite done. Oh my God. All right. So let's see. Two planes that are not parallel intersect in a straight line, and the angle between the two planes is defined as the acute angle between their normal vectors. All right, well, we already had some practice finding the angles between vectors. What we could do is we could do the dot product between them and then solve for cosine of theta. So for example, let's take the planes that we were looking at last time. This one has a normal vector of 1, 1, 0. This has a normal vector of 0, 1, 1. And so if we look at the dot product of these, remember that the dot product is the magnitude of the first times the magnitude of the second times cosine of the angle between them. So what we can do is we can divide by these and take inverse cosine. So we have cosine inverse of n1 dot n2 divided by the magnitude of n1 and the magnitude of n2. All right, and whatever this is, this will give us our theta. Okay, so let's see, n1 dot n2, we actually already did that in the previous problem, right? That's how we figured out they weren't orthogonal or parallel. n1 dot n2 from earlier ended up giving us a 1 right here. So this will be 1. let's see, the magnitude of N1 and N2 is actually the same number. What is the magnitude of both N1 and N2? Root 2, that's right. So we have root 2 for this, root 2 for this. This is cosine inverse of 1/2, and that's going to give us pi over 3, or 60 degrees if you like. This will be the angle between the two of them here. All right, let's see. Oh my God, we really are out of time here. So I guess just like usual, I'll try to finish up these notes and post them later today once class is over. What's on the page behind is the distance between a point and a plane right here. All right, I'm sorry I wasn't able to get through all this. I felt like I was going pretty fast too. All right, anyways, I will see you guys all on Monday, where we will be looking at some different three-dimensional shapes besides points and, lines and planes. So see you guys then.
Bye, Dr. Manley. Thank you.
Yeah, see you later.
Thank you,
Have a good
Professor.
weekend.
Bye. Have a good weekend.
Thank you.
Thank you, Dr. Manley.
Yep, see you guys later.
Professor, where did the
Can you
notes get
put
posted?
the last page? Thank you.
I think someone was starting to ask a question. What was that?
Where do the notes get posted, please?
I post them on the same page I put all of the lecture recordings.
Okay, thank you.
And these notes will be posted before the lecture quizzes due, right?
I'm sorry, you're speaking really softly. What did you say?
I said these notes will be posted before the lecture quizzes due, right?
I'm really sorry. Can you maybe type it in the chat? I don't think your audio is.
He's asking if the notes can be posted before the assignment is due.
Oh yeah, I'm gonna once I'm done teaching my next class, I'll go and write them and then put them up. Yeah, see you later. Yeah, what's up?
You mentioned the whole break math joke. I know I forgot the name right now. I heard in Spanish. Like the basic principles of mathematics are like the rules of which were based in basic math or physics. Then sides of a triangle is 180 degrees. Has math ever been broken before? Because I know physics has we've had classical physics, and then Einstein came up and was like, yeah, that kind of works, but not really. And then we have special relativity. Has math ever been broken before? To some extent.
The way I like to imagine math is like Monopoly. So in Monopoly, you kind of have the basic rules that everyone accepts, right? Have you ever played Monopoly, by the way? Okay. But then sometimes there are people who like to do things like put a few $100s on free parking or something like that. And as long as everyone who's playing the game agrees with those rules, then they're totally fine. So effectively, math is just a game that you play. You can use the axioms, like you were saying, and kind of build them, combine them with logic to make more things. Math is any system where you could do that, just as long as everyone agrees on the rules. The thing about 0 equaling 1 is that in pretty much every game, that's just going to negate everything. And that's going to make all numbers, it's going to make pretty much any system of math crash. So you don't really want to do that no matter what.
All right. Thank you, Tony.
I would argue maybe calculus over statistics is the original breaking of math.
I don't know. I mean, it's mathematically consistent. There's nothing wrong with it. They were more expanding math by doing things like limits and infinitesimals.
It's kind of crazy, like how they did all the proofs and hard numbers before calculators and everything.
Oh yeah, yeah, like Gauss and stuff had to do logs of numbers without a calculator by using the Taylor series. It's it's really terrible.
Yeah, it's pretty impressive.
Thank you, Tony. How did you get inverse cosine of the dot product of the magnitude equals 0?
Oh, sorry, that's theta.
Oh, okay.
Theta, yeah, it's not 0. All right, guys, I will see you all later.